Hi everyone. So this lesson, lesson 1.2, is going to determine the present value, and we're going to look at compound discount. So in our last lesson, we learned what the future value was of an investment that had compound interest. Okay, so that was called the future value, or FV. Previously, when we did simple interest, it was called S. You can call it either term you want, as I've mentioned, but both of them are actually the same value. Similarly, we can actually work backwards. So instead of determining the future value, we could determine how much we need to invest now to have a certain value in the future if we know the interest rate and how often it's being compounded. Okay, so that's called the present value. So previously that was called P. Alternatively, you can call it PV, which means present value. Personally, I like the FV and PV terms. They seem more straightforward than using S and P, but you can use either formula. And when you're looking at doing quizzes and tests, I'll usually give you a formula sheet that you can use while you're writing it. Obviously, we can't do that in person, but you can have it with you while you're testing. So the formula, okay, remember we started with it for future value, was FV, the future value, is equal to your present value, and that's multiplied by 1 plus your interest rate per period. Remember the difference between this one and simple interest, it's just your interest rate calculated per period, and that looks at how many compounding periods you have in a year, and also what your annual interest rate or nominal interest rate is. And that is raised to the exponent n. N is your total number of compounding periods. The difference between this and the calculation for I was that when you did the total number of compounding periods, that was the total amount of time you plan to have the investment. So when you were using compounding periods to calculate your interest rate per period, that looked at number of compounding periods just in a 1-year period, because your interest rate, your nominal interest rate that they'll give you, let's say it's 4%, is per year or per annum. Okay, so meanwhile, this total one is if you have an investment for 10 years, the N would look at your total amount of compounding periods over that entire 10-year span. So if you want to derive this formula, all right, if you remember, when we did our review, and we also did some rearranging in our last course, we start with the formula. The future value is equal to the present value multiplied by 1 plus the periodic interest rate, I, raised to the exponent n. So remember, we want to solve for this PV term, okay? Because that's the only term that we have that we want to have left on the right side. So to do that, just like in any other term, okay, you have this entire term, 1 plus I to the exponent n. That's all one term, okay? There's multiple variables in it, but you can divide both sides by that whole term, all right? And it will still cancel, okay? So if you look at this and you divide by 1 plus I, in brackets, all to the exponent n, you end up with, on the left side, the future value divided by 1 plus I to the exponent n equals the present value multiplied by 1 plus I to the n here and 1 plus I to the n in the denominator. And since those are the same terms, just like any other term, they also can cancel. So that actually cancels and just becomes 1. Okay, so what we're left with is that our future value divided by 1 plus the periodic interest rate raised to the exponent n is equal to the present value. So just rearranging it, all I did was move everything from the left side to the right side and everything from the right side to the left side. I get my final formula. The present value is equal to the future value divided by 1 plus the periodic interest rate raised to the exponent n. So I don't expect you to know how to derive this formula. I'm just showing you how we did it, okay? So this formula would be one that would be provided to you, okay? So let's look at an example. Find the principal or present value, okay, that will amount in 6 years to $17,715.61 at 10% interest, PA or per annum, compounded annually. Okay, so we can start with our formula. Okay, our present value is equal to our future value divided by 1 plus periodic interest rate raised to the exponent n. So now we're starting to get into a lot of variables. So when I have these problems, and as you saw in the previous lecture, I like to list out what I have and what I need to calculate. Okay, so we know our future value is $17,715.61. Okay, we know that our interest rate per year per annum, remember, that's our nominal interest rate, J, is equal to 10%, okay? Which, if you want to convert that to a decimal, remember we have to use decimals in these formulas, it's 10 divided by 100, removing the percentage sign, which is 0.10. The next term we know that it's compounded annually, right? So that means that if it's annually, there's only one time it's compounded. So that means our compounding periods per year, M, is equal to 1. And now if we want to look at a couple calculations here, okay, we know that our total number of compounding periods, right? We know that it's 6 years, okay? So our total number of compounding periods, N, is equal to the number of compounding periods per year, M, multiplied by the total time, or the number of years that we're compounding, okay? Or the number of periods, you can call it. I wrote years, you can also call it number of periods. Okay, so we know that M is equal to 1 because it's just compounded annually. And that's multiplied by the number of periods. Well, we know we have 6 years, right? So our total number of years is 6. So that gives us a value for our total number of compounding periods of 6. In our last term, okay, we have everything else except we don't have I. But we do know that I, so our periodic interest rate, is equal to our nominal interest rate divided by our number of compounding periods per year. Remember, because we want to figure out what that rate is each time it's compounded in a year. In this instance, it's simple, right? Because we know that our nominal interest rate is 10% or 0.10, and we only have one compounding period per year, it's annually. So it's just 0.10 divided by 1, which is just 0.10. So now we have all the terms we need. So we can substitute them into the formula. This is why I like to look at every term in a separate side, so sitting here on the right side, so that then I can just take those values and substitute them in. Okay, so what that is, that means our present value is equal to our future value, $17,715.61, divided by 1 plus 0.10, because that's our term I, and that's raised to the exponent 6. Okay, so if you calculate that out, you get a present value of $10,000. Okay, so the method will be the same when you're calculating all of these formulas, and as we continue to do these formulas, you'll notice that there are a lot of terms. So if you're finding that going through all these terms can seem a little bit daunting, you can always keep the sheet with you that has what each term means from a previous lecture, okay, or a formula sheet with you beside you, just so you can follow along with what each of these letters means, okay? So let's look at another example. Find the present value of $6,836.56 due in 9 years, and it's at 6% interest per annum, right? Remember, that's yearly, compounded quarterly. Okay, so we start with our formula. Present value is equal to our future value divided by 1 plus I raised to the exponent n. So now I look on the right side, I'm going to start writing the terms that I know. Well, I know that my future value is $6,836.56. I know that my interest rate, or my nominal interest rate, J, is 6%. Which is equal to 6 divided by 100, removing the percentage sign, which is equal to 0.06. I also know, okay, my number of compounding periods per year, M, because it was given that it's compounded quarterly. So if you remember quarterly, that means every 3 months, so our number of compounding periods per year is 4, all right? So next, our next term, you can kind of see where this is going. right? You have the base variables, the future value, your nominal interest rate, and your number of compounding periods per year. So your next term would be looking at something that's in this formula, okay? Something that we haven't calculated in the formula. So if you look at the periodic interest rate, I, remember that's equal to your nominal interest rate divided by your number of compounding periods per year. And we just calculated both of those, right? We just figured them out given the question. We didn't even calculate them, as I mentioned. They were just in the question. So we can substitute those in and we get 0.06 divided by 4 because there's 4 compounding periods. And that gives you an answer of 0.015. Okay? Lastly, we have our total number of compounding periods, n. So that's equal to our number of compounding periods per year, which is the term m, multiplied by the number of years for this loan, okay? Or I guess this is an investment. So if you substitute those values in, we know that the number of compounding periods is 4 per year, and we know that it's due in 9 years. So what that means is our total number of compounding periods is 36. So now we have everything. We have the future value, we have our periodic interest rate, and we have our total number of compounding periods. So we can substitute everything into the formula. Our present value is equal to $6,836.56, that's the future value, divided by 1 plus 0.015, the periodic interest rate, raised to the exponent 36, because that's our total number of periods. So one thing to notice here is that as you raise something to an exponent, the higher the exponent, if the number is greater than 1, okay, it's not a decimal, the larger that number gets. It's exponential, okay? So as you increase the number of quarterly or number of periods in a year, this is quarterly, the previous question was annually, you notice that this value in the denominator is just going to get larger. So what that means is as you have more and more and more compounding periods, you're earning interest more and more and more often on the interest that you've already gained, right? Because this isn't simple interest, it's compound interest. So you're earning interest not just on the amount of money you placed in at the start, but also the interest that you're making on that money each time your investment is compounded, okay? So if you calculate this value out, you see that your present value is $4,000, okay? So you can see in those 9 years, you made over $2,800, right? So that's more than a 50% increase in that period of time. So as it's invested or as it's compounded more frequently, you make more money off those investments, okay? Your interest rate goes further. So let's look at one more example before we move on to a different topic. Find the present value of $2,000 due in 3 years and 9 months at 8% per annum, interest compounded quarterly. Okay, so again, start with your formula. Present value is equal to your future value divided by 1 plus your periodic interest rate raised to the exponent n. So what do we know? Okay, we know our future value is $2,000. Okay, we know that our nominal interest rate is 8%. Remember, that has to be converted to a decimal, so it's 8 divided by 100, removing the percentage sign, which equals 0.08. We know the number of compounding periods per year. Again, it's provided just like last question as quarterly. So what that means is every 3 months. So our total number of compounding periods per year is 4. Okay, so now we can look at calculating our periodic interest rate. Our periodic interest rate is equal to our nominal interest rate, or the interest rate over the entire year, divided by our number of compounding periods per year. So that is equal to 0.08, the number we just calculated, divided by our number of compounding periods, which is 4. So that gives you a value of 0.02. So now we can look at the number of compounding periods, the total number of compounding periods. Okay, so we're looking here, it says it's 3 years and 9 months. Okay, so 9 months all right, if you're trying to convert everything to years, this formula is the number of compounding periods per year multiplied by the number of years. So if you look here, okay, we know that our number of compounding periods per year is 4, and our number of years is 3 years and 9 months. So if we converted that all to years, okay, our number of years is equal to 3, plus we have to convert that 9 months to years. So it's 9 months divided by the total number of months in a year. So if we add those together, we get a total number of years of 3.75, because 9 divided by 12 is 0.75. Okay, so all I'm doing is picture that I'm taking that, all right, as a fraction and converting it just to a decimal. Okay, because we want to figure it out. It all needs to be in one term. We can't have it in years and months, or months and weeks, or weeks and days. Okay, it all has to be in one term. And because your number of compounding periods, m, is per year, then this second term should be in years. Okay, so if you substitute that in, we get our total number is equal to 4, right, number of compounding periods per year multiplied by 3.75 years, and we get an answer of 15. So now if we substitute all these values in, we get our present value is equal to our future value, $2,000, divided by 1 plus 0.02, our periodic interest rate, and that's raised to the exponent 15, our total number of compounding periods. And if you calculate that out, you get a present value of $1,486.03. Okay? So now I want to talk about some applications. Okay? So one good example is when governments or businesses, they borrow money and it's for longer than a year. Usually they'll provide what's called a promissory note. And that's basically a fancy term for a loan, right? They'll apply for a loan to get that money. And that note is actually a written promise by one party to pay a certain sum of money to another party. They can be with or without interest. Usually they're with interest. And if it's with interest, it's using the same compound interest formula that we've been using to calculate over the last lecture and this lecture. Okay? The benefit to these is that if they're long-term notes, they can be bought or sold at any time before maturity. So let's say they decided to pay their loan back early. All right? And what I want to do is figure out what that value is, depending on if you're giving that person a loan, and let's say it's a family member, and you're giving them an IOU, right? Or a loan agreement, and it's without interest. You're just lending them some money, maybe they need a few bucks, right? And in 2 years, they'll pay it back. Or you give them a loan, especially if it's to a business, okay? And they owe you that money at a certain amount of interest later on, okay? And maybe they decide to pay it back early. If they do, that's actually, you have to calculate that present value, okay, at that period in time, since it's not at the very end date. And that's actually known as the discounted value or proceeds, okay? So those terms we'll use interchangeably when we do these calculations. There's two types of notes that I want to talk about, non-interest bearing and interest bearing notes. So a non-interest bearing note, the value that's provided, or whatever the loan is, $4,000, that's the future value. So basically, when you have that note, the value that the note is for has an amount of interest calculated in it already. So that value is the value it is at the very end. So let's say 3 or 4 years down the road when you have to pay the loan back. So it is the future value. So the name implies that there's no interest involved, but all it's saying is there's no interest value on kind of the face of that note, okay? So that interest is actually calculated within the total value, in this instance, as an example, $4,000. Interest-bearing notes, okay, the value provided is the present value. So the value in that note is not including that interest, okay? So it's not inherently built in. It usually has an interest rate associated with it. So when the loan comes due a couple years down the road, you have to actually calculate that future value, because the value you're given on that loan is actually the present value. So they're just a little bit different in how you consider them. It'll be provided usually in a question, whether it's interest-bearing or non-interest-bearing. So this difference would be the main item you need to know when you're approaching one of those questions. So it may sound a little bit confusing. I think our best choice is to do some examples. I'm going to start with non-interest-bearing notes, and then we'll look at a few examples with interest-bearing notes. Starting with a non-interest-bearing note, let's look at an example. Determine the discounted value of a non-interest-bearing note for $15,000, discounted 2 years and 3 months before its due date, at 9% interest per annum compounded monthly. Remember, with a non-interest-bearing note, the value provided is the future value because the interest is inherently built into that number. So if you're paying it back early or it's being discounted early, you have to subtract the interest value from it and determine the present value at that period of time that's earlier than when it would otherwise be due or otherwise come to its maturity date. So that means we need to determine the present value 2 years and 3 months before the due date. So we start with our formula. Present value is equal to our future value divided by 1 plus the periodic interest rate to the exponent n. And let's look at what values we know. Well, we know it's a non-interest bearing note, so we know that this value of $15,000 is the future value. Next, if we look at the interest rate, the nominal interest rate provided in the question is 9% per annum. And remember, converting that equals 9 divided by 100, removing the percentage sign, which is 0.09. Next, we'll calculate the number of compounding periods per year. It's provided in the question that it's compounded monthly. So if it's compounded monthly, that means you'd have 12 periods in a year because there's 12 months in a year. Next, now that we know J and M, we can calculate the periodic interest rate, which is J divided by M. And that is equal to 0.09 divided by the number of periods in the year, compounding periods, 12, and that is 0.0075. Lastly, the last term we need is the total number of compounding periods, N, and that's equal to the number of years for the term, okay, or in this instance, the number of years it was early, multiplied by number of compounding periods per year. So the number of years, if you'll notice from the question, okay, I'll highlight it in blue, is given as both years and months. So we have to convert the months portion into years. So we have 3 months, and that is divided by 12 because there's 12 months in a year, and you get 0.25. So your value for N is then equal to 2 because there's 2 years plus that 0.25, right, for the 3 months. And that's multiplied by the number of compounding periods per year, which is 12. And if you calculate that out, you get a total number of compounding periods of 27. So substituting all of these values in, your present value is then equal to your future value, $15,000, divided by 1 plus 0.0075, the periodic interest rate, and that's raised to the exponent 27. So your present value is $12,259.56. All right, so you can see that it was reduced from what its face value was in the non-interest bearing note because it was paid back at an earlier date. So let's look at one more example of a non-interest bearing note. A 4-year non-interest bearing promissory note for $6,000 was dated August 31st, 2015, and earned interest at 6% per annum compounded monthly. Determine the proceeds of the note if it was discounted on October 31st, 2016. So remember, okay, this is a non-interest bearing note, which means that this value is actually the future value, okay, which means we need to calculate the present value, okay, at this date, October 31st, 2016. So to do that, first, I'm going to start with the formula, okay? Your present value is equal to your future value divided by 1 plus the periodic interest rate I raised to the exponent n, the total number of compounding periods. So let's look at the information that we know. We know the future value is $6,000, and that's because this is a non-interest bearing note. Okay. The nominal interest rate is 6% provided in the question, which is the same as 6 divided by 100, removing the percentage sign, which equals 0.06. Our number of compounding periods per year, again, provided in the question, it was compounded monthly. So if it's monthly, okay, that means that our total number of compounding periods per year is 12. So now we can calculate the periodic interest rate, I, because that's equal to J divided by M, which is 0.06 divided by 12, which is equal to 0.005. So our last item, okay, is the total number of compounding periods. This is where it gets interesting, all right? So our question noted it as a 4-year promissory note. And the note was dated August 31st, 2015, okay? So that means, okay, that was the day that the note was initiated. So the maturity date, or the date that this future value is valid for, right? Because remember, in a non-interest bearing note, that value of $6,000 is the future value, or in other words, the value 4 years from now. So if you consider it, okay, I'm going to draw one of these graphs again. We have August 31st, 2015. That's the starting date. And that means 4 years from then, we have 2015 to 2016, 2016 to 2017, 2017 to 2018, and 2018 to 2019. So 4 years from then would be August 31st, 2019. Now that, August 31st, remember, since this is non-interest bearing, that is when the $6,000 is equal, right? If you waited until 4 years from when this note was initiated, you would have to pay that full value of $6,000. But they're paying it back at a different time. They're paying it back October 31st, 2016, so somewhere back here. So you actually have to figure out what this timeline is from the future value point, which is the value we know, backwards to this October 31st, 2016 date. Okay, and that's because that is the actual period of time where you're saving the interest, right? So you're converting from the future value of $6,000 on August 31st, 2019, 4 years after the note was initiated, to the time where it was come due when you're trying to determine the proceeds for, and that was on October 31st, 2016. So if you convert that, all right, you have to consider, you can consider it using your hands, all right? You have October 31st, you have November and December in 2016. You're going to have all of 2017 and all of 2018. So if I count this, okay, and this is compounded monthly. So if we look at 2016, actually I'm going to write it here on the right side. You have 2 months. You have all of 2017 and all of 2018. Okay, because it comes due in 2019. So 2018 is 12 months as well. And 2019, you've got January, February, March, April, May, June, July, and August, because it's the end of August. So that means you have 8 months in 2019. So if you add all of these up, you end up with a total amount of time of 34 months. Okay? So that's the amount of time to consider when you're doing your present value calculation. Okay? So when we look back and we're trying to calculate n, okay, n is equal to the number of years, okay, multiplied by m, the number of compounding periods. So you can either use this value of 34 months, and that's only because it's compounded monthly, or you can calculate it like this. So n would be equal to a number of years. So we have 34 months, and we have to convert that to years, right? So you divide it by 12, because there's 12 months in a year. Then you have to multiply that, I'm going to remove this arrow, by m, which is the number of compounding periods, which is 12. And if you calculate that out, you'll get an answer of 34 compounding periods. All right, so remember, when you're looking at this problem, you had to actually work backwards to get to that solution. I'll draw the blue line back, okay? So now with all this information, you have to substitute that into your formula to find the present value that they would pay, since they're paying their loan back early. So their present value is equal to the future value, $6,000, divided by 1 plus your periodic interest rate, 0.005, and that's all to the exponent 34. So if you calculate that, all right, calculate at the same time as you get a present value of $5,064.13. Okay, so if they pay it back 34 months early, they only have to pay $5,064.13 instead of the full $6,000. So interest-bearing notes are a little bit different. So with an interest-bearing note, okay, the value of the note is actually the present value. So in order to determine a discounted value, so let's say you have your present value, okay, and it's due in 4 years, just like our last question, and you want to pay it back in 2 years instead. Well, first, you have to do 2 steps. It's a little more involved. The first step is using the interest rate at the initial period of time. You have to determine the future value at the time of maturity, or when the loan would come due. All right? Then using that future value, okay, you have to find the present value at whatever time you want to pay it back early. In this instance, it was 2 years. Using that period's current interest rate, right? Because remember, the interest rate fluctuates. We did an example in our last lecture where the interest rate changed, right? And if you look at items like the Bank of Canada, every year they're constantly reviewing their interest rates and changing them. So you actually have to do both those steps. The first step, calculating the future value, using that interest rate when it was initiated, and then going from the future value back to the present value that you're currently at whenever you're looking to pay it off at whatever that revised interest rate is. So we're going to look at 3 different examples of interest-bearing notes. The first example, determine the proceeds of a promissory note for $3,600 with interest at 6% per annum compounded quarterly. It was issued September 1st, 2014 and is due on June 1st, 2020. It was discounted on December 31st, 2016 at 8% interest per annum compounded semi-annually. So there's a couple things you can notice here. Notice there's 2 interest rates, okay? The promissory note interest rate when it was initiated, 6% per annum compounded quarterly, and the interest when it was discounted or paid, which was 8% per annum compounded semi-annually, okay? So if you start with a timeline, all right, we're looking at, it was issued September 1st, 2014, and it's due June 1st, 2020. And it was discounted, or in other words, the time you're calculating in your second step, on December 31st, 2016. Okay, so remember, since this is an interest-bearing note, this value of $3,600 is actually your present value. So it's your value at the starting point. So first, we have to calculate the future value, okay, as of June 1st, 2020. So if we look at that first, all right, we're going to look at our formula. The future value is equal to the present value times 1 plus the periodic interest rate to the exponent n. Now, what items do we know? We know our present value, which is $3,600. And we know at this period in time, when the note was initiated, what the nominal interest rate was, which was 6%, which is equal to 6 divided by 100, removing the percentage sign, which is equal to 0.06. And we know it was compounded quarterly. So our number of compounding periods per year, since it's quarterly, must be 4. So now we can solve for our periodic interest rate, I, which is equal to J divided by M, which is 0.06 divided by 4, which is equal to 0.015. So our last item, all right, is going to be to determine the total number of compounding periods. And that's equal to the number of years multiplied by the number of compounding periods per year. So again, we're going from September 1st, 2014 to June 1st, 2020. So we know we'll count September, October, November, and December of 2014. Again, I'll note that here. So that's 4 months. Then we can count 2015, 2016, 2017, 2018, and 2019. So 2015 to 2019, that's 5 years. Okay. And then lastly, in 2020, we can count January, February, March, April, and May. We can't count June because it's June 1st, so that's 5 months. So 2020 is 5 months. So our total is 5 years and 5 months. 5 years and 9 months, sorry. So if we plug that in, we'll convert the months in our equation. So we have n is equal to 5 years plus our 9 months divided by 12. So we can convert 9 months to years, right? Because there's 12 months in a year. And that's multiplied by the number of compounding periods a year, which is 4. If we calculate this out, okay, we get 23. So n is equal to 23 compounding periods. So if we calculate, now we know all the variables. We can calculate our future value. And that's equal to our present value, which is $3,600, multiplied by 1 plus 0.015 to the exponent 23. So if we calculate that out, we get an answer of $5,070.16. So that, all right, is the future value as of June 1st, 2020. Okay, so now we have to take that and we have to convert it back to December 31st, 2016, using our current interest rate as of that period of time, right, which is a different interest rate and different compounding periods. Okay, so again, we're going to start with the same. We got to use the formula. This one is a little bit different since we're trying to find the present value. So we use our other formula, the present value formula. Present value is equal to future value divided by 1 plus the periodic interest rate to the exponent n. So the values that we know that our future value is $5,070.16. We know our nominal interest rate at this period is 8%, which is the same as 8 divided by 100, removing the percentage sign, which is 0.08. And in this instance, our number of compounding periods is compounded semi-annually, which means our number of compounding periods per year is 2. So we can calculate first our periodic interest rate, which is J divided by M, which is 0.08 divided by 2, which is 0.04. Now we can calculate, okay, our total number of compounding periods. We know it's December 31st, 2016 to June 1st, 2020. So if we go back, okay, I'm going back up top here again for this. In 2016, there's 0 because it's the very last day of the year, December 31st. Then we have all of 2017, 2018, and 2019, which is 3 years. And then in 2020, just like in the past, we'd have 5 months, January, February, March, April, and May. We don't count June because it's June 1st, 2020. So in 2020, we have 5 months. So our total period here is 3 years and 5 months. So substituting that down in our formula for the total amount of compounding periods, remember, it's the number of years multiplied by the compounding periods per year, m. And that's equal to 3 plus our 5 months, which we have to convert to years. So 5, and you divide it by 12, since it's in months. Okay, and that's multiplied by 2. So you end up with, if you add these together, or if you multiply these together, is you have 6.833 compounding periods. Okay, it's not a round number, right? And that's okay. So now if you substitute all of these values in, your present value is equal to your future value, $5,070.16, divided by 1 plus your periodic interest rate, in this case 0.04, and that's all raised to the exponent 6.833. If you plug those numbers in, I'm doing it at the same time as you, you end up with an answer, okay, of $3,878.22. Notice it's a little different, okay, than my answer that I have sitting here. The big reason for that, all right, is because I use 6.833. If you were to do it without removing the decimals, okay, so if you were to leave it as 6.833 and it's a repeating decimal, then you'd actually get the answer that I have written, okay? I'll test it right now as we're talking. And you get that answer, okay, $3,852.90. So it makes a little bit of difference in dollars when it comes to rounding, okay? So let's look at a second example. Again, this is the second of 3 examples for interest-bearing notes. A 5-year note for $8,000 bearing interest at 6% per annum compounded monthly is discounted 2 years and 6 months before the due date at 5% per annum interest compounded semi-annually. Determine the discounted value of the note. So again, we're looking at interest-bearing note, so we first have to calculate the future value of the note when it would be due, and then work backwards to calculate the present value at the time it's being discounted or paid. So, starting with our graph again, we have year 0, okay, and that is when you have the present value of the note, $8,000. It's a 5-year note, so that means you get to year 5, and we're going to calculate that future value. And the time it's being discounted is 2 years and 6 months before the due date, which is actually right in the middle, okay? So that's year, I'm going to call it 2.5, since 2 years and 6 months is 2.5 years. So that's the point that we're trying to figure out what the present value is, okay? So we're going to start, just like we did in the last one, calculating the future value first. So a future value is equal to the present value times 1 plus the periodic interest rate to the exponent n. We know the present value is $8,000, and we know the nominal interest rate at this point in time is 6%, provided in the question, which is the same as 6 divided by 100, removing the percentage sign, which is 0.06. Our number of compounding periods per year in this, again, given in the question, it's compounded monthly at this period in time. So that means M is 12. So putting these together, solving for the periodic interest rate, that's equal to J divided by M, which is equal to 0.06 divided by 12, which is 0.005. All right. So last step is we need the total number of compounding periods, N, which is the number of years multiplied by M, okay, the number of compounding periods per year. Well, we know it's a 5-year note, so N is equal to 5 years multiplied by 12 compounding periods per year, which is equal to 60. So our future value, now that we have all the information, we can calculate it, is equal to our present value, $8,000 times 1 plus 0.005, right, our periodic interest rate. And that's all to the exponent 60, okay, our total number of compounding periods. If you calculate that value out, you'll get $10,790.80. Okay, so that is your future value sitting at year 5, $10,790.80. So now we have to take that and discount it back to find the present value at year 2.5. So now that we're finding the present value, remember the formula is different. The present value is equal to our future value divided by 1 plus our interest rate, periodic interest rate, to the exponent n. So what do we know in this formula? We know our future value, okay, that's equal to $10,790.80. We know at this period of time, our nominal interest rate, remember it's different, it's 5% this time, so it's 5%, which is equal to 5 divided by 100, moving the percentage sign, which is equal to 0.05. We know our number of interest rates per year, or number of compounding periods per year, sorry, since it's given as semi-annually, so that means our number of compounding periods is 2. So, again, we can calculate our interest rate I, okay, which is equal to J divided by M, which is equal to 0.05 divided by 2, which equals 0.025. Our last step, N, the total number of compounding periods, okay, is equal to the number of years multiplied by M, which is our compounding periods per year. So our number of years, remember it's discounted 2 years and 6 months before the due date. 6 months is 1/2 of a year, okay? So N is equal to 2.5 years multiplied by 2, okay? Because we have 2 compounding periods per year. That gives us a value of N of 5. Substituting all of these values in, now that we have I, N, and our future value, our present value is equal to $10,790.80 divided by 1 plus 0.025, our periodic interest rate, and that's raised to our total number of compounding periods for the exponent, which is 5. And if you calculate that out, you'll get an answer of $9,537.50. Okay, so that's the value that they have to pay back if they're paying it 2 years and 6 months or 2.5 years early. Okay, so our last example. Find the proceeds of a $5,000 7-year note bearing interest at 8% per annum compounded quarterly, and it's discounted 2.5 years after the date of issue. Okay, keep that in mind for later. At 6% per annum interest compounded monthly. So let's start with our timetable again. So this is an interest-bearing note. So starting at year 0, your starting point, that means your present value of your note, since it's interest bearing, is $5,000. It's a 7-year note, so that means we first have to go to year 7 to find the future value. Then we have to go back to the point that it's discounted, right, to figure out what that value is then using the new interest rate. So it was discounted 2.5 years after the date of issue, meaning it was actually discounted at year 2.5. Okay, so that means there's 2.5 years from the date it was issued to here, but there's actually then 4.5 years from the date that it was discounted to the date of maturity, which is where we're going to find the future value. Okay, so that 4.5 years is going to be important because it's going to be our time frame for our second step when we calculate our present value. So let's look at our first calculation, taking our present value and finding the future value at the date of maturity, or year 7. So we know that our future value is equal to our present value times 1 plus the periodic interest rate to the exponent n. So we know our present value is equal to $5,000. We know at this point our nominal interest rate provided in the question is 8%, which is equal to 8 divided by 100, removing the percentage sign, which is equal to 0.08. Our number of compounding periods per year, m, this is compounded quarterly, so that means m is equal to 4. So now calculating our periodic interest rate, I, that's equal to j divided by m, which is equal to 0.08 divided by 4, because it's quarterly, which equals 0.02. Our last item to calculate, our total number of compounding periods, n, is equal to the number of years multiplied by m, our total number, or our number of compounding periods per year. So our number of years, it's given that it's a 7-year note, remember? And remember we drew this graph and we're trying to find year number 7. So we substitute this in, we have 7 years multiplied by 4 compounding periods per year, and we get an answer of 28. So if we substitute all these into our formula, our future value is equal to our present value, $5,000, multiplied by 1 plus 0.02, and that's all raised to the exponent 28. If we do that calculation, we get an answer of $8,705.12. So now we have the future value, okay, at year 7. It's $8,705.12. So now we need to work backwards to year 2.5, right? Because that's when it was discounted, to find what the value is at that point in time. So looking at that, now we need to find a present value. So the present value is equal to our future value divided by 1 plus the periodic interest rate to the exponent n. So in this case, we know our future value. It's equal to $8,705.12. We know our interest rate now. Remember, we have to look at a different interest rate, what the current interest rate is, highlighted in blue. And it's 6% per annum, and it's compounded monthly. So if we take that into account, J, our interest rate, is 6%, is equal to 6 divided by 100, removing the percentage sign, is equal to 0.06. Our number of compounding periods per year, m, again, it's compounded monthly, so that means m is equal to 12. Putting these together, our periodic interest rate is equal to j divided by m, which is equal to 0.06 divided by 12, which equals 0.005. Our last step, n, okay, is simple. It's the number of years multiplied by our number of compounding periods per year. Again, this is why I said it's simple, because we already know it's 4.5 years, okay, before the maturity date, which is year number 7. We calculated that earlier. So we can substitute that in, 4.5 years multiplied by 12, because our number of compounding periods per year is 12, and we get an answer of 54. So now we can substitute all these values in and solve. So our present value is equal to our future value, $8,705.12, divided by 1 plus our periodic interest rate, 0.005, and that's to the exponent 54, our total number of compounding periods. If you substitute that in, you get a value of $6,649.78. So that's the amount they would pay back at this period of time, which is year 2.5. So that was all that I had for this lecture. These are the practice problems you should look at. Again, if you have questions, please feel free to let me know, or please ask the questions on Thursday during our tutorial session at 10:30. If you have questions from the textbook, you can ask those, or you can ask specific questions from the lecture. I'll try my best to pull up each of those kind of as you need them. Okay, so thanks everybody.